Hello, Vijayashree ma'am. Hello, Vijayashree ma'am.
Yes, ma'am. Yes, ma'am.
Good evening, ma'am. Good evening. Hearty welcome to SNS College of Engineering, ma'am.
Good evening, ma'am. Thank you.
Hearty
Thank you so much.
welcome to this FTP.
Thank you, ma'am.
Ma'am, shall we start the session, ma'am?
Yeah, sure, ma'am.
Okay, ma'am. Right, let me introduce you to the like participants.
Yes,
Uh,
please.
Dear participants, we have a very eminent person, Madam Vijayashree Chinnasamy. Miss Vijayashree Chinnasamy completed her bachelor degree in electrical and electronics engineering and master's degree in energy engineering from Anna University. Her academic pursuits laid the foundation for her deep expertise in energy systems and sustainable practices. She began her career as an assistant professor, where she not only imparted knowledge to aspiring engineers but also demonstrated exceptional leadership and mentoring skills. Her passion for making a tangible impact in the field of sustainability led her to transition into consulting, where she joined Deloitte's Sustainability and Climate Change team. At Deloitte, Vijayashree has excelled in driving impactful projects across energy, environment, and climate change domains. Her expertise includes greenhouse gas accounting, environmental and social due diligence, EHS compliance, and decarbonization strategies. With over a decade of experience, she has been instrumental in advising organizations on adopting sustainable solutions and meeting their ESG goals. Hearty welcome, ma'am. You can take the platform.
Thank you, ma'am. Thank you. Is my screen visible?
Yeah, it's visible, ma'am.
Okay. Good evening, everyone. It's an absolute pleasure to be here with all of you for today's faculty development program. First, let me extend my gratitude to the organizers for this opportunity and to all of you for your dedicating your time to discuss this topic. So, this topic is just not academically significant, but also critically relevant in day-to-day today's world. Energy storage technology for climate resilience. Uh, so, this is the contents which we are going to see now. Introduction about the role of energy storage in climate resilience and its significance, type of energy storage technologies, and role of energy storage in renewable energy integration and technological advances, challenges in day-to-day energy storage implementation. So let me give a short intro of this. Today I would like to discuss a pressing and multifaceted issue that affects us all, the intersection of global energy demand, greenhouse gas emission, and the escalating impact of climate change on energy infrastructure. The energy sector has long been a cornerstone of economic growth and development, but its role is increasingly becoming one of the critical concerns here. As we delve into this topic, we must reflect on how our choices today will shape the sustainability of our energy systems and their resilience against future climate changes. The demand for energy has been on an upward trajectory worldwide, a trend that's driven primarily by economic expansion and the growth of the global population. While energy consumption supports progress and human development, it also comes at a significant cost. Comes in zero cost, right? So the sector is a major contributor to greenhouse gas emission. You all have to agree on this. Energy sector is the major contributor to the greenhouse gas emission all over the world. And with the current pattern of consumption, production, Emission from energy are projected to continue to rise. What's more troubling is that in recent years, the long term trend of a gradual decarbonization has taken a step back due to significant resurgence in coal burning. This shift undermines decades of progress towards cleaner energy sources and threatens to intensify the climate crisis. Climate change with its associated impact is not a distant threat. It's a present day challenge, right? What we are facing in real world. The energy infrastructure we depend on is increasingly susceptible to climate hazards. And these challenges are intensifying in day to day life. A progressive increase in global temperature, along with growing frequency and severity of extreme weather events, poses significant risk to energy production and transmission. Changing precipitation pattern also affect the supply of water, which is a crucial resource for cooling and hydropower generation. So this underscores that the energy sector does not exist in isolation, but is deeply connected to a broader ecological and climatic systems. The supply of fossil fuels remains vulnerable to disruption from climate-related phenomena such as hurricanes, flood, wildfires, which we are seeing in daily life, right? Which can cripple supply chains and diminish production capacities. Similarly, the reliability of thermal and hydropower generation faces mounting challenges as shifting weather patterns alter the availability of water and the condition needed for effective power generation. Despite the gravity of these challenges, there are adaptation strategies. For every problem, we have a solution, right? Similarly, we have adaptation strategies also that can be employed to make energy system more resilient. From integrating climate adaptation measures into energy planning to improving grid infrastructure, proactive measures can strengthen the sector's capacity to withstand climatic disruptions. However, these adaptations are not with their cost. To align with the goal of limiting global temperature rise to below 2 degrees Celsius compared to pre-industrial level, it is estimated that investment of 190 to 900 billion USD per year will be required on the supply side alone. So this is a significant financial commitment, but it is necessary to secure a future where energy system can endure and thrive despite climate uncertainties. Infrastructure investment are not short-term projects. Energy infrastructure in particular tend to remain in service for at least 30 years once it's built. So this means that the decision we make over the next couple of decades will be pivotal. They will determine whether our energy sector will steer towards or away from 2-degree future. If we choose to maintain the status or delay action, we run the risk of unlocking a path that leads to severe climate impacts, high operational cost, and reduced energy security. The traditional energy grid, which have served as the backbone of our energy distribution, are particularly vulnerable to their centralized nature. This dependence on extensive infrastructure make them prone to widespread of blackouts during natural disaster. As we have witnessed this during our Chennai flood, there are blackout of power for even a week or 10 days, which we struggled a lot without power. So these are our upfront and in front natural calamities which we are witnessing in nowadays. So, in the face of increasingly severe climate events, this model is becoming unattainable. We need to consider alternatives such as decentralized and more resilient energy systems, which can offer greater flexibility and reliability in the face of disruptions. current scenario of India is facing now. So, India's ambitious vision to achieve net zero emission by 2070 demonstrates its proactive approach to tackling climate change while fostering sustainable development. To reach this milestone, India has set a pivotal short-term goals including increasing its renewable energy capacity of 500 gigawatt by 2030, fulfilling its 50% of energy requirement from renewable sources, and reducing the emission intensity of GDP by 45% from 2005 level. This commitment also includes a significant reduction of 1 billion tons of cumulative emission by 2030. So positioning India as a global leader in clean energy transition. These targets are critical not just mitigating climate change but also for building a resilient energy infrastructure that supports India's growing economy and energy demands. So achieving these goals requires a multifaceted strategy. Integrating renewable energy into the grid is key, and the energy storage technology will play a vital role in managing the variability of solar and wind power. So grid balancing service and advanced demand side management measures. So these are some of the measures which can help optimize energy distribution, ensuring reliability and efficiency. So moreover, operating thermal power plants flexibility to complement renewable generation is another essential step in maintaining a grid stability. Together, these measures will enable India to meet its climate commitments, enhance energy security, and driven innovation in the renewable energy sector by adopting these approaches. India can lead by example, inspiring global action towards a sustainable and resilient future. So, according to the National Energy Plan set by 2023, India has an energy storage target for 2026 to 2027. As of now, India has set a target only for pumped storage plant of 47.65 gigawatt and battery energy storage system of 34.72 gigawatt hour of energy till a period of 2026 to 2027. So this is the target as of now India has for the energy storage system. Moving on to next, why do we go for energy storage system? What is the significance beyond that? Energy storage technologies are pivotal for transforming the global energy into more sustainable, resilient and energy model. So here are some significant features. Why do we go for or why do we invest in energy storage system? So most of the developing and developed countries are ready to invest in their energy storage system rather than producing it. Why do we go for it? Balancing renewable energy variability. So renewable energy sources like solar and wind are inherently intermittent. Solar power depend on sunlight and wind rely on wind speed. So both of which are not constant. Say for example, solar panels generate electricity only during the daytime and wind turbines may be idle during calm weather only. So energy storage acts as a buffer by capturing surplus energy during the peak generation time like midday for solar and storing it for use during the periods of low generation like nighttime or the cloudy days. So this capability ensures that renewable energy is not wasted and can meet energy demand during peak demand even when the source is not available. Ensuring grid stability and reliability. A stable power grid requires a constant balance between the energy supply and demand. So without energy storage, this balance becomes increasingly challenging with higher shares of renewable due to their fluctuating output. So storage systems smooth output these fluctuations, providing energy when demand spikes or generation drops. They prevent power outages and blackouts by maintaining the required grid frequency and voltage stability. Say, for instance, during peak demand hour, stored energy can be released to the grid to stabilize the grid, ensuring uninterrupted power supply and reliable performance. So next comes the supporting decarbonization goal. So when we invest in energy storage system, indirectly we support our decarbonization goal. Like the global shift towards achieving net zero emission relies heavily on integrating renewable energy sources into the energy mix. However, the variability of renewables can limit their adoption. Energy storage technology resolve this issue by enabling the storage and dispatch of renewable energy whenever needed, making it possible to replace the fossil fuels effectively. So, by ensuring a steady and reliable flow on clean energy, storage technologies accelerate decarbonization and help achieve climate targets like reducing GHG emissions and keeping the global temperature rise below 2 degrees. Uh, Next is the enhancing energy independence. Energy independence, it just refers to reducing the reliance on imported fossil fuels or centralized energy systems, which are vulnerable to supply disruption. So, energy storage here provides a decentralized solution by enabling local storage and utilization of renewable energy. So, communities and nations can maintain energy availability during fuel shortages, geopolitical conflicts, or wars or disruption in centralized energy grids. It empowers consumers with greater control over their energy use, fostering resilience and security. Next comes the optimization cost for utilities and consumers. Energy cost fluctuate throughout the day. As you know, energy cost will increase day by day with the higher prices during peak demand periods. Storage system enable energy to be stored during peak of peak times when electricity is cheaper and used during peak hours. So this load shifting reduces cost also for utilities by avoiding the need for expensive fast ramping power plants to meet peak demand. So consumers like us also benefit from lower electricity bills due to efficient energy use and reduced reliance on peak hour electricity rates. Next is the building disaster resilience. As climate change intensifies, the frequency and severity of natural disasters like hurricanes, flood, these are increasing. We are witnessing in our day-to-day life how flood is affecting everyone's life. So these events often disrupt traditional energy systems, causing widespread blackouts. Energy storage technology is especially when paired with renewable sources like solar panels provide critical backup power to essential services like hospitals, emergencies, shelters, and communication systems during disaster times. So, this resilience is invaluable in mitigating the impact of extreme weather and ensuring public safety, like hospitals or the emergency shelters. So, next is the driving innovation and emergency emerging technology. Energy storage is a cornerstone for successful implementation of emerging technologies like EV vehicle, microgrids, smart grids, as you all know. So these innovation powered by energy storage pave the way for more sustainable and technologically advanced energy ecosystem. So, till now we have seen why we need for energy system in our daily activities or in our current scenario. What makes the country or what makes the nation to push uh, towards the energy storage system investment? So, high investment is required to store energy, which in turn helps in reducing the cost of our daily activities and the GHG emissions also. So let's move on to next slide. Next types of energy storage systems. In the pursuit of climate resilience, energy storage systems are vital for enhancing the stability and reliability of power grid. They play a significant role in integrating renewable energy and balancing supply and demand. In that fortifying infrastructure against the disruptions. So here are some types of energy storage system: mechanical, chemical, electrical, thermal energy, electrochemical. So when we see about mechanical energy storage, such as pumped hydro storage and flywheels, are highly efficient in converting and storing energy through the gravitational and kinetic forces. So these systems excel in providing a rapid response for grid stabilization, making them invaluable for mitigating the fluctuations. Next is the chemical storage, which primarily includes the battery and hydrogen systems, leverages chemical reactions to store the energies. So this method enables high density energy retention, offering transportability and versatility. So batteries, for instance, are essential not only for portable application but also for large scale grid storage. Nowadays, most of the renewable power plant like solar are utilizing batteries for storing back the excess amount of energy which are produced during non-peak hours. So, uh, so batteries are essential for the large scale grid storage as well. They can help in smooth out intermittent power and enhance energy security. And the supercapacitors offer unique advance with the rapid charge and discharge capability. They are ideal for applications that require immediate energy bursts such as frequency regulation and short-term power supply. So this play a critical role in energy system that demands fast responsiveness. So next is the thermal energy storage, which captures excessive energy, which is the heat energy, and it can be converted back into the electrical energy or utilized directly for heating and cooling purposes, which is widely used mostly in the industrial purposes or district heating and cooling purposes. Uh, Nowadays, in big countries like Dubai, where they need both heating and cooling, which they have a centralized district cooling and heating system. In those places, these thermal energy storage system play a very crucial role in providing the uninterrupted power supply. So these thermal energy storage system is especially useful in managing peak energy loads and improving the energy efficiency of buildings and industrial processes. Integration of these storage technologies is fundamental to building a climate resilient energy infrastructure by enabling a more consistent and efficient energy use. They support the transition to renewable energy sources and bolster the grid ability to withstand climate related disruptions. The advancement and strategic deployment of these systems will be pivotal in achieving sustainable energy goals and mitigating impact of climate change. So these are some examples of energy storage technologies where we have electrochemical, thermal, electrical, chemical and mechanical. In the forthcoming slides, we are going to see some of the energy storage technologies which are currently in research, and in some of the developed countries, they started using the energy storage technologies also. As I said in the before slide, even India started investing in energy storage system. Only India has focused only on two side. One is pumped hydro storage system, another one is BES, battery energy storage system. So India is focusing only on these two part, and others are in the research stage, and it need more cost effective also. So it need more investment to get implemented in the future year. So in that battery storage system, we are going to see the lithium ion batteries. So this batteries have become synonymous with energy storage due to their extensive applications. So and their exceptional performance also. From powering our mobile device to revolutioning the even EV vehicle industry and providing grid stability. Nowadays, most of the EV vehicles are using lithium ion battery. So, this technology is a core for many sectors. So, as you know, the heart of lithium ion batteries is their electrochemical reaction. So these batteries are composed of primarily components like anode, cathode, electrode, and the anode typically made of graphite, and cathode it is built up of lithium cobalt oxide and some other similar material also. So when a battery charges, lithium ions move from cathode to anode through the electrode. So during discharge, these ions move back to the cathode. So this is a simple battery, how lithium battery works, as you all know well about this. So this helps in generating the electric current, which will be used to power the devices. So one of the biggest advantage of using this lithium ion battery is their high energy density. So this means that this can store a significant amount of energy in a compact space, making them for ideal for portable electronics smartphones, laptops, and electric vehicles. Another key importance of this lithium battery is their long life cycle. Unlike many other batteries, this lithium ion batteries offer a relatively longer lifespan. Typically, say for example, 500 to maximum of 2000 charging cycles. So this long cycle life makes them a cost-effective choice for application that require frequent charging and discharging. Next is their efficiency and their fast charging. Lithium-ion batteries boast an impressive efficiency rate of over 90%. Means that most of the energy used to charge the battery is retained. Additionally, advancements in technology have made fast charging capabilities, allowing a device and vehicle to recharge significantly faster than before. As you all know, we are using mobile, and most of the people have moved from petrol or diesel vehicle to the electric vehicles, and they know the charging time also. Despite of the before era, nowadays even the mobile phones and the electric vehicles are getting charged so fast, and then they're lightweight and versatile compared to alternative lead acid battery. This lithium batteries are lighter weighted, which is critical for application in many of the applications. So their flexibility in design also makes them adaptable to variable size and shape, expanding their range of application. Most of the smartphones, tablets, laptops, we are using lithium ion battery to power the portable devices. So their ability to hold a substantial amount of energy in small form of factor ensures their reliability. And in the even EV vehicles, perhaps one of the most transformative application of lithium ion technology is in the automotive industry. You all believe or not, EVs are driving the global shift towards cleaner energy and reduced carbon emission. So, lithium ion batteries offer the range, recharging speed, and the performance needed the widespread adoption of electric vehicles. Uh, as you all know, some of the key manufacturers like Tesla, Nissan, even BMW have led the way in integrating these batteries in their vehicles nowadays. Next is the lithium ion technology is also crucial for stabilizing power grid, especially as the renewable energy sources like solar and wind become more prevalent. These energy sources are intermittent and unpredictable. By using large scale lithium battery systems to surplus amount of energy during high generation periods. So we can release it during high peak period or high demand period, or when power generation is low. So this will ensure the grid stability and the reliability, where we can get the uninterrupted power supplies. And we can use this as a backup for power system also. The uninterrupted UPS or the home energy storage system, such as those offered by companies like uh, Tesla or the LG Chem, these system provide reliable power during outages and help household to maximize the use of solar energy. So most of the people who are using solar power panels for producing the energy, they are using the lithium ion battery for storing the generated power. So even after seeing after so many of its key features, we have challenges in lithium ion batteries too. Uh, its raw material. Their production of lithium ion battery rely on materials like lithium, cobalt, and nickel, which are limited and often come from regions with complex geopolitical and ethical issues. So mining these materials can have a significant environmental and social impact as well. And this in turn goes to safety concern. Why we are saying this will create a social impact? Um, Lithium ion batteries, while generally safe, can be prone to thermal runaway. If damaged or improperly handled, this can lead to overheating, fire, and even explosion can happen in rare cases. So proper design and safety measures have helped mitigate these risks, but they remain a concern, especially in low quality or counterfeit batteries. When we talk about the environmental impact, the disposal and recycling of the lithium ion batteries pose environmental challenges. The chemicals used in these batteries can be harmful if not properly managed. So, recycling programs are emerging to address this. But the industry still faces hurdle in creating efficient, cost-effective recycling processes. This circular economy or recycling of batteries is still a concern in all the developing and developed countries. And although the price have decreased significantly over the years, lithium ion batteries are still relatively expensive compared to some other energy storage option. So this cost can be a barrier to entry for application where budget constraints are tight. So when we see about the future of this lithium ion battery, these batteries looks promising as research continue to push the boundaries. Innovations include improvements in battery chemistry like development of solid state batteries that promise even higher energy densities and safety. Furthermore, enhanced recycling technologies and the use of alternative, more sustainable materials will help to mitigate these some of the current challenges. Next is the flow batteries. Flow batteries are a type of rechargeable battery that store energy in liquid form, liquid electrolytes. So, unlike traditional batteries, these energy is stored in solid electrodes. Flow batteries use two separate electrodes that flow through a cell track where the energy conversion takes place. And the two main type of flow batteries which are using nowadays are vanadium redox flow battery and a zinc bromine flow batteries. So these are among flow batteries. These are there in the market nowadays. Uh, as you all know, key component of these flow batteries are electrolyte solutions, cell stack, pumps, and balancing systems. So this will ensure a smooth and circulation of electrolytes between the tank and cell stacks. Uh, as you all know, flow batteries operates like electrochemical reaction between the two liquid electrolytes. During charging, energy is supplied to the cell, causing the oxidation at one electrode and the reduction at the other. This movement of electron creates an electric current. So during discharge, the process reverses. A simple process. But a crucial feature of the flow batteries is their ability to decouple energy storage from power output. This is unlike conventional batteries where energy capacity and power capacity are often linked. In flow battery, size of the electrolyte tank determines the total energy capacity, while the number of cell stacks impact the power output. Um, the significant or the advantages in flow batteries are their uh, long span or long duration energy storage. It's one of its most significant benefits of flow battery is their ability to provide energy over long period from hours even to days. So this is particularly valuable for balancing out intermittent renewable energy sources, which may produce excess power and which can be utilized for non-peak hours. And their flow batteries can be scaled up or down by simply increasing the size of the electrolyte tanks and the number of cells. So this allows for customized energy storage solutions tailored to specific needs, whether it's a small residential system or even if it is a very big or large utility scale project. Um, the flow batteries are known for their life cycle or long lifespan, the ability to handle deep discharges without significant degradation. They can operate for more than 10,000 charging cycles, making them ideal for application require, requiring frequent cycling. The liquid nature of the electrolyte in the flow batteries means that they are less prone to overheating, thermal runaway, and fire hazards. Uh, just before some time, I have told these are the drawbacks of the lithium ion batteries. So, if we see the flow batteries, so these are their advantages. So, compared to solid state batteries like lithium ion, these are their advantages. Additionally, the absence of flammable components also reduce risk in the case of malfunctions. So these batteries can be made with non-toxic and recyclable materials, reducing their environmental footprint. As I told before, vanadium, a commonly used element in vanadium flow batteries, is abundant and can be reused multiple times without degradation, so enhancing the stability of the technology. When we talk about the application of this flow batteries, they are excellent for grid stabilization, where they store excess power during the peak hours. This helps to balance supply and demand, reducing the need for fossil fuel based peaking plants and supporting a higher integration of renewable energy sources. As renewable energies are often variable, flow batteries can store the excess energy generated by solar panels and wind turbines, ensuring a steady supply during the non-generation periods. This boosts the reliability and adoption of renewable energy system, making them a key technology for transitioning to a low carbon grid. Flow batteries are suited for microgrids, especially those in remote or off-grid areas where consistent power supply is crucial. Their ability to be easily scaled and their long lifespan make them ideal for providing stable long-term power solution in these settings. And they provide a reliable power backup solution for critical infrastructures like hospital data centers, emergency services, etc. So their ability to provide power for extended periods ensures that essential operations continue during blackouts or disruptions. When we talk about the challenges in the flow batteries, one of the major challenges, their relatively high upfront cost compared to other energy storage technology like lithium-ion battery. However, their long span and lower maintenance costs can offset these expense over time. So, due to their need for large electrolyte tank, flow battery can take up more physical space than solid state batteries. So this can be a limiting factor for application in areas where space is a constraint. So technology involves pumps, tanks, and complex fluid circulation system, which can make the system more complex and potentially more costly to maintain compared to simpler battery solutions. And the future of flow battery is promising as research and development continue to advance. Innovations in materials and electrolyte solutions such as organic and ion-based electrolyte aim to improve performance, cost effectiveness, and environmental impact. So improvement in manufacturing and design are expected to reduce cost and make flow batteries more competitive with traditional storage technologies. Next, we move on to thermal storage system. So, as you all know, storing the thermal energy. This technology allows us to store energy in the form of heat or cold. So, providing a flexible and efficient means to manage energy demand, enhance grid stability, and optimize the renewable energy utilization. The thermal energy storage, it's nothing but a storing of excess amount of thermal energy, whether in the form of a heat or a cold for later use. It operates in the principle of capturing the energy when it is abundant and storing it for a period when demand is higher or generation is low. This thermal energy storage can be categorized into a sensible heat storage or latent heat storage. So, under sensible heat storage, this involves heating or cooling a medium, uh, such as water or rocks or molten salt, without changing its phase. So, this energy is stored as in the form of a temperature, change in temperature of storage material. In turn, when we talk about latent heat storage, this type utilizes the phase change material, which absorbs and release energy during the process of changing from one phase to another, such as from solid to liquid or liquid to gas, either in the way. So, this method allows for most compact storage because this phase change material can store energy at a constant temperature. So, main feature of this thermal energy storage is it can be utilized for multiple functions like heating, cooling, electricity generation. As I said before, this heating and cooling can be used in many of the high-rise buildings. So this versatility makes it adaptable to a variety of sectors from residential to commercial buildings to large-scale industrial processes as well, and even to utility-scale power plants as well. So this thermal energy storage is particularly suited for large-scale energy storage needs, such as in district heating system or solar thermal power plants. By storing energy at a scale, it can contribute to balancing supply and demand at the grid level and support energy transition goals. So one of the most appealing aspects of this thermal energy storage is its use of abundant non-toxic eco-friendly materials like water, rocks or salt. So this makes it an environmentally responsible solution compared to other storage methods that may rely on rare or hazardous material for their making. So, this can be the thermal energy storage can be predominantly used in concentrated solar power plants where molten salts are used as storage medium. So, these salts can absorb and store solar energy during peak sunlight hours and release it when the sun is not shining. so thereby providing a continuous power supply. So this capacity enhances the reliability of solar as when it is integrating renewable energy into the energy mix. Next comes the heating and cooling in buildings. Um, mm, Most of the thermal energy storage in nowadays are used for heating and cooling in buildings. So instead of relying on the electricity for heating or cooling the building, we are relying on the thermal energy storage, where thermal energy can be stored in any form, which in turn can be used either for heating or cooling the building. So this can be integrated into residential or commercial buildings to manage heating and cooling needs efficiently. For example, chilled water or ice storage system can be used to store cooling energy during peak off hours and release it during peak demand hours. So this helps to reduce the energy cost and lessens the strain on the grid. The industries with high energy demand, such as chemical manufacturing, food processing, metal, cement industries, can benefit from these thermal energy storage systems. So these systems can store high temperature heat that can be used when needed, so leading to energy savings and improved operational efficiencies. So these two have challenges. Even though it is eco-friendly or not non-polluting, one of the challenge with this thermal energy is the inherent energy loss when converting stored heat into electricity. The process of converting thermal to electrical energy, typically through steam turbine or other heat to electricity conversion methods, is not efficient. So this can lead to some loss of stored energy during power generation. Next is the space constraints. Thermal energy storage, this system often requires significant physical space for the storage of materials and infrastructure. So, for example, large scale thermal storage power plant or system using molten salt needed sizable storage tank or the reservoir for storing the salts. So, this can be a limitation for the application in densely populated or the urban areas where space is the constraint. So, thermal storage is promising technology that holds substantial potential for supporting a more sustainable and resilient energy future. By leveraging and versatility, the scalability and eco-friendly nature of thermal energy storage, we can make significant stride towards reducing energy waste, enhancing energy security, and integrating more renewable energy sources into our grid. So, while there are challenges such as efficiency losses and space requirement, ongoing research and technological advancements continue to address these issues. Innovation in materials science are paving the way for more efficient and compact phase change material, while engineering advancement aim to optimize heat conversion systems to reduce the energy losses. So next comes the pumped hydro storage system, where most of the countries are using this system as their energy storage. Even in India, we are using this pumped hydro storage system. So one of the most established and effective energy storage system, we can say this pumped hydro storage system. So despite the emergence of newer storage solution, so this remains a cornerstone in the field of energy storage, helping to enhance the grid reliability and the integrated renewable energy sources effectively. As you all know, pumped hydro storage is an energy which is stored in the form of potential energy. So that leverages gravitational potential energy to store and release electricity. So it involves two reservoirs located at different elevation, upper reservoir, lower reservoir, where when electricity demand is low, excess energy is excess electricity is used to pump the water from lower reservoir to upper reservoir, converting the electricity energy into gravitational potential energy. So when electricity demand rises, water flows back and flows back down from the upper reservoir to lower reservoir, passing through the turbine to generate the electricity. This is a simple logic behind the hydro storage system. So this process effectively turns stored water into a powerful energy storage that can be deployed when needed. Uh, this is one of the very proven technology. This has been in use for many decades and continue to be reliable form of energy storage, accounting for over nearly 90% of the global energy storage capacity. As I said before, even in India, most of the developed countries are using this form of energy storage as their capacity. So this long track record demonstrates its ability to provide consistent performance and reliability, making it a tried and true solution for energy management. Another one of the important standout characteristics of this pumped hydro is its high round trip efficiency, which typically ranges from 70% to 85%. This means a significant portion of the energy used to pump the water is recovered back when it flows back down through the turbine to generate electricity. So this high efficiency makes this hydro storage a cost-effective storage solution over its operational lifespan. Next is their capability, their large-scale capability, which is best suited for the energy storage. This technology is capable of storing large amount of energy, making it ideal for balancing large electricity grids. This capability supports the utility scale applications, enabling power system operates to manage grid stability, reduce reliance on fossil fuels, and enhance the integration of renewable energy sources also. So when we talk about the application, one of the primary uses of this pumped hydro storage is to stabilize the grid and balance the fluctuation that come with renewable energy sources. Wind and solar power are subject to variable generation due to weather changes, leading to potential instability in the power grid. So this pumped hydro storage can restore excess energy generated during periods of high renewable production and release it during times of low production, thus ensuring a consistent and reliable power supply. Uh, it is invaluable for utilities in managing peak loads periods when electricity demand surges. So, by releasing stored water during peak hours, utilities can meet high electricity demand without having to rely on expensive and carbon intensive peaking power plant. So this result in cost saving for both utilities and the consumers as well and reduce the overall carbon footprint of the power generation. So this is also used as a power backup during outages also. Pumped hydro storage can provide a dependable power backup during supply power outage or grid failures or during even the maintenance. The technology's ability to quickly respond to sudden change in demand or power loss ensures that critical infrastructure and services can continue to operate, enhancing overall grid resilience. When we talk about the challenges faced by this pumped hydro storage, one of the significant challenge of this pumped hydro is its reliance on specific geographical condition. It requires suitable terrain with the availability of two reservoirs at different elevation, which is not feasible in all regions. A site need to have necessary topography and water resource to support the construction and operation of the system. So this geographical limitation restricts widespread adoption of the storage technology and requires careful selection of site and assessment. And it also requires a high capital investment And this construction of pumped hydro facilities is capital intensive due to significant infrastructure needed, including construction of dams, reservoirs, turbines. So this high initial cost can be a barrier to new project. Although the long operational life of this is 30 to 50 years, but this allows for a cost amortization over time. Despite these challenges, pumped hydro storage remains a key player in global energy storage landscape due to its proven technology efficiency and large-scale capabilities. So, with the growing emphasis on renewable energy integration and grid stability, this can play an essential role in modern power system as well. Uh, Furthermore, this pumped hydro storage is a tried and true energy storage technology that continue to offer significant benefit for grid management, renewable energy integration, and peak load management as well. So next comes the compressed air energy storage system. This is a unique characteristic and potential for bulk energy storage. So this is an innovative method for storing energy, offering a practical solution to energy management that challenges and contributing to a more resilient and efficient power grid. As you all know, this compressed air energy storage is nothing but the storing of energy in a compressed form, compressing air and storing it in underground caverns or tanks during a period of low energy demand. So when energy is needed, the compressed air is released, heated, and then expanded through turbine which generates its electricity. So this process involves converting the electrical energy into mechanical energy by compressing that and storing it for later use. When we talk about the important features, so one of the significant advantage of this system is its ability to store energy on a large scale. This make it an excellent solution for bulk energy storage, allowing it for utilities to maintain a stable supply during periods of high energy demand or when renewable energy production is low. The technology can store 10 or even 100 of megawatt hour of energy, which is essential for this grid management at a scale. The system have a long operational life and experience minimal performance degradation over time. So unlike some battery storage systems that can pose or that can lose capacity with each cycle, this compressed air energy storage can maintain its efficiency over several decades. So this durability uh, translate to reliable and long-term use, providing significant value to energy operators. So it is flexible and can complement renewable energy sources, which are often intermittent when renewable energy production exceeds energy can be used to compress and store the air during period of high energy demand or low renewable energy generation. The stored air can be released and can be utilized for the power generation. So main application of this system is utility scale energy storage, grid stability, and peak saving, renewable energy integration. It is well suited for utility scale energy storage projects because of its ability to store large quantity of energy and deliver it efficiently when needed. This makes it an effective tool for energy providers to balance the supply and demand. Another key role of the system is to help stabilize the power grid and reduce the peak load by storing energy during peak demand hours. So it can reduce strain on power plant and prevent grid overload. So this capability improves the overall reliability and its ability to withstand fluctuation in energy demand. Um, Another thing is that it plays an essential role in integrating renewable energy sources such as wind and solar into the grid. Because of this, sources are often intermittent. The system can store excess energy when generation is high and release it when generation dips. This helps maintain a stable supply of electricity, making the use of renewable power supply. But the challenge faced by this energy storage system is its efficiency. It is a valuable energy storage method. It does have a lower energy efficiency range compared to other storage technologies. Typically, the system have a round trip efficiency of less than or 40 to 60 percentage, meaning that some energy is lost in the compression and expansion process. So this lower efficiency can impact the economic feasibility of projects and require careful consideration when evaluating storage options. So another main challenges with this is it relies on specific geological formation to store compressed air. So suitable underground storage sites include salt caverns, depleted natural gas reservoirs, and aquifers are needed. So the availability and geological suitability of this formation can limit the location where these facilities can be built. In addition, development of underground storage site may require significant survey and regulatory approval from the government, adding it to the complexity of the project planning. So, despite of these challenges, this storage system is an essential technology for energy storage and grid management. Moreover, they are under being researched to improve its efficiency. For example, the use of adiabatic compression, where the heat generated during the compression is captured and reused. This can enhance the overall efficiency of this compressed air energy storage system. So, this approach, known as adiabatic CAS, seeks to minimize energy loss and makes the system more economically viable and efficient option. So, although it faces us, many challenges, this is also a proven technology, which is an emerging technology where most of the researchers are taking hand this energy storage system, where they can give a effective tool for managing the energy and contributing to a sustainable and resilient power grid. Next one is the flywheel option. So, this technology is not widely discussed as lithium ion batteries or pumped hydro storage offers unique benefits that makes it highly effective for specific applications where rapid responses and high power output are critical. This flywheel is based on straightforward yet highly efficient principle. It stores energy in the form of rotational kinetic energy. A flywheel is essentially a rotating mass that spins at very high speed with the vacuum or a low resistance environment. So when energy is needed, flywheel's rotational energy is converted back into the electricity through generator. So this process involves a combination of mechanical and energy system. But the key feature of these flywheel are their high power output and their rapid response. One of the defining characteristics of flywheel is their ability to deliver a quick burst of power, making them ideal for application where a fast response is necessary. They can go from standstill to full speed in just a fraction of seconds. So, which is valuable for grid stabilization and frequency regulation as well. So, this rapid response capability is unmatched by many other storage technology, making flywheel perfect for handling a sudden shift in power demand. And it is also known for its efficiency. Very high round trip efficiency, typically ranging from 85% to 95, which is comparable to or even better than some of the best battery technologies. The energy stored in flywheel is released with minimal losses, resulting in fewer inefficiency over time. So another significant advantage in is their long life cycle. Flywheel can last for decades with minimal performance degradation, which make them cost effective. Next is their maintenance, low maintenance. This have fewer moving parts compared to other mechanical energy storage technology, which translate to reduce wear and tear. So, many systems are designed with magnetic bearings that eliminate friction, thereby extending the life of the flywheel and minimizing the maintenance cost. This flywheel are mostly utilized in the grid stabilization. They are excellent for balancing supply and demand on the grid. When there is excess power, flywheel can store it, and in turn, during the demand period, the flywheel is released, providing immediate support to the grid and stabilizing frequency fluctuation. So, this capability is essential for maintaining grid reliability. They are used in UPS also, UPS system to provide power backup during the power outages. Because of their rapid response, rapid discharge, flywheel can seamlessly bridge the gap between the loss of power and activation of backup generators or other energy sources. So this application is particularly useful for data centers, hospitals where immediate response is needed, and in critical infrastructure that require immediate response for UPS system. Flywheel can help address the variability of renewable energy sources like wind and solar by storing excess energy generated during peak hour and releasing it during lulls. Flywheel support a more balanced and reliable energy supply. Though it has several advantages, these flywheel energy storage also face some difficulties because of its high cost and energy density limitations and their safety considerations. The primary barrier to this widespread adoption of flywheel energy storage is its initial capital cost. The technology, especially high performance flywheel designed for grid scale storage, requires significant investment in both materials and in engineering also. So this makes flywheel system more expensive upfront compared to other energy storage solutions. However, this cost can be offset over time due to its long lifespan and minimal maintenance. While flywheel excel in power output and rapid response, their energy density and the amount of energy they can store relative to their size and weight. So this can be lower than that of other storage solution like battery and pumped hydro. This makes the flywheel better suited for application where high power and rapid response are more crucial. Next is comes the safety consideration. Flywheel operate at very high rotational speed and there are safety concerns related to their potential to release energy if damaged. Although modern flywheel systems are designed with safety mechanisms and containment system to prevent catastrophic failure, handling and maintaining these systems require strict safety protocols prescribed by our government MNRE. Overcoming these challenges, advancement in material science and engineering are continuously enhancing the capability of flywheel system. So the use of high strength and composite materials for flywheel itself allow for higher rotational speed and greater energy storage capacity. Magnetic bearing and vacuum environment further reduce its friction and energy loss. So As a thing, their unique characteristics make them especially valuable for grid stabilization, renewable energy integration, and uninterrupted power supply. As we advance toward a future powered by clean and renewable energy, flywheel are set to play a significant role in their resilience. Next comes the hydrogen energy storage. Um, Hydrogen storage, while not as a mainstream as lithium battery or pumped storage, offers unique advantage that position it as a transformative energy storage solution. Its versatility and environmental benefit make it indispensable for achieving global energy transition goals, particularly in integrating renewable energy sources and decarbonizing key sectors. Uh, so when we talk about its features, hydrogen storage involve converting surplus electricity into hydrogen gas via electrolysis. It involves a process where water is split into hydrogen and oxygen using electricity. Hydrogen produced can be stored in pressurized tank and in a liquid form, liquid hydrogen container, or even absorbed into advanced material. When energy is required, the stored hydrogen is converted back into electricity using fuel cells or combustion turbines. So main feature of this hydrogen storage is their versatility across its application. So hydrogen is more than an energy carrier. It's cornerstone for various application from hydrogen as from the grid energy stabilization to powering fuel cell vehicles. So hydrogen can be deployed across sectors, bridging the gap between renewable energy generation and the end use consumption. So its ability to convert it into electricity, heat, or mechanical power adds to its utility. When produced using renewable energy, hydrogen generation is virtually emission free. Unlike conventional fuels, its use in fuel cells emits only water vapor, making it an environmental friendly solution for energy storage and consumption. But hydrogen is particularly well suited for long duration energy storage. Unlike batteries, uh, we discussed before, which are typically limited to hours or days of storage, hydrogen can store energy for even weeks or even for months without significant losses. So this makes it balancing seasonal fluctuations in renewable production. Um, Thus, hydrogen storage can be used in grid energy storage and load balancing. This storage enables the capture of excess renewable during peak hours and it can be used during non-peak hours. The stored energy can be used for balancing the demand. Next is fuel for hydrogen powered vehicles. Hydrogen storage system supply fuel for growing range of hydrogen powered vehicles, including car, bus, and even trains in some of the developed countries. So, with rapid refueling capabilities and long driving ranges, hydrogen vehicle offer a sustainable alternative to fossil fuel based transportation. So, hydrogen can replace natural gas and other fossil fuel in industrial processes as well, including steel production, ammonia synthesis, and high temperature heating. So, it also has a potential as an energy storage for remote and off-grid applications. Though the energy storage hydrogen energy storage has significant application and environment friendly. It is also facing some of the challenges because of its high cost constraints. The production and utilization of hydrogen currently involves significant cost, particularly for electrolytes and fuel cell technologies. So, hydrogen's low volumetric energy density means that it requires compression, liquefaction, or advanced chemical carriers for storage. So this process can be energy intensive and costly, complicating the logistics of large scale hydrogen deployment. Next is its infrastructure. Robust hydrogen infrastructure spanning protection, storage, and distribution remains underdeveloped in many regions. So, by overcoming these challenges, this hydrogen storage can be used in the future with its potential to decarbonize energy system, enhance its grid stability. Next is the supercapacitor. Unlike the conventional batteries, which stores energy chemically, a supercapacitor store energy electrostatically. So this is also known as the ultra capacitor or electric double layer capacitor, where energy storage that use electric fields to store energy rather than chemical reactions. So by this consists of two conductive plates separated by an electrode. When voltage is applied, electric field is created and leading to a rapid storage of energy. Uh, when we talk about the key features, high power density, long life cycle, and lightweight and it's compact. One of the standout feature of supercapacitor is their ability to deliver and absorb energy rapidly. So this high power density makes them suitable for application requiring burst of power demand. Supercapacitors are also known for its exceptional longevity. When traditional batteries typically degrade over time, lost capacity after few hundred or few thousand charge cycle, supercapacitor can last for millions of cycles with minimal performance degradation. Supercapacitors are lightweight and compact, making them ideal for application where space and weight are important consideration. So this can be utilized for power backup for electronic devices. Supercapacitor are a good source of power back for most of the electronic devices due to their rapid charge and discharge capabilities. Supercapacitors can provide a quick energy boost to the smart devices. Renewable regenerating braking system in vehicles. So this plays an important role in braking system which are used in electric and hybrid vehicle to recover energy that would otherwise be lost during braking. The energy generated is stored quickly in the supercapacitor and released when needed, also providing power to accelerate the vehicle or support other vehicle functions. And supercapacitor are highly effective for grid applications, particularly in situations that require quick energy burst to maintain the stability. And it also faces challenges because of its low energy density compared to the batteries. While supercapacitor excel in power density and longevity, they fall short when it comes to energy density. The amount of energy they can store relative to their volume or weight is lower than that of batteries. So this means that supercapacitor are best suited for short duration, duration energy storage and are not ideal for applications that require long-term power storage. Next is the cost constraint. Cost of supercapacitor can be higher than that of conventional batteries, which can be limiting factor for a widespread adoption. Next is due to their relatively low energy density, supercapacitor are best utilized in niche applications where their rapid change and discharge cycle, long cycle life, and compact design offer the most value. So, apart from or despite these challenges, the future of supercapacitor is also a promising one, where researchers are actively exploring advanced materials and design to improve their efficiency, energy density, and cost effectiveness. For example, use of graphene and carbon nanotubes as electrode material is paving the way for supercapacitor that offer higher energy densities. So additionally, hybrid supercapacitor system that combined supercapacitor with battery or other storage technologies are being developed. So these systems can harness the fast charging and discharging of supercapacitor while benefiting from high energy storage of batteries. Next one is the solid state batteries. These are poised to address many of the challenges faced by conventional energy storage system. As we all know, the solid state battery are an evolution of traditional lithium ion battery, but with a major difference. They use a solid electrolyte instead of liquid or gel type of electrolyte, which is formed in the lithium ion battery. So this key change offers numerous advantages, including higher energy density, enhanced safety, and greater longevity. Uh, the key important feature of these batteries are high energy density when compared to other storage batteries. And the advantage of the solid is their potential for much higher energy density compared to traditional lithium ion batteries. So this could translate to longer lasting power in EV vehicles and consumer electronics, as well as increased storage capacity for renewable energy systems. So for EVs, this means a higher driving range on a single charge or shorter charging times. When we talk about the safety, is a primary concern with conventional lithium battery, which are flammable and prone to a thermal runaway. A chain reaction that can lead to overheating and even fire may happen. So solid cell batteries address this risk by utilizing solid electrolyte that is non-flammable and is much less prone to breaking down. So this enhanced safety feature make this solid state batteries mold as a more reliable option. This especially for applications in the EV vehicle or other high stakes environments. Solid state batteries exhibit reduced degradation over time compared to their electrolyte counterparts. So this means that they can last longer and withstand more charging and discharging cycles. Their applications include next-gen EV vehicles. Solid-state batteries are considered the holy grail of EV market. Their potential to offer higher energy density and faster charging times could revolutionize this EV industry, making the EV vehicles more attractive to the consumers. So the increased safety and consideration of solid state technology address the common concern of battery life and potential hazards. So even some smartphones, laptops, consumer electronics rely heavily on this battery that are both reliable and long lasting. So next comes the long duration energy storage systems. With the increasing a need for energy efficient energy storage solutions to balance renewable energy production, solid state batteries offer a compelling option. So their ability to operate with energy density and stability over time makes them suitable for grid storage and backup system. These also face some challenges like high manufacturing cost and technical complexities, their limited commercialization at scale, and material and manufacturing challenges. So, while potential benefits are substantial, the path of mass adoption of solid state batteries is not without its hurdles. So, one of the most significant challenges is high cost of production. Next comes the commercial scale production. This remains limited. The transition from lab scale to industrial scale manufacturing involves overcoming obstacles such as maintaining uniformity and consistency. Identifying suitable material for a solid electrolyte that are both efficient and cost effective. This may pose a serious challenge in this type of cells. So the materials must have high iconic conductivity to allow or efficient energy transfer while also being stable over long period of use. So future of this solid state batteries look promising, driven by ongoing research and development. So companies and research institutions are around the world exploring various materials and production methods to overcome current limitations. So for example, or the researchers are looking at a new types of ceramic electrolytes and sulfide based materials that can offer both high iconic conductivity and mechanical stability. So, innovation in manufacturing, such as roll to roll processing and advanced depositioning technology, may help to reduce the cost of this production. So, this is a simple comparison where energy storage technologies have compared. This comparative analysis of various balancing technology option as given, and out of this pumped hydro storage can provide long duration storage up to 10 hours. So battery storage is emerging but is yet to become commercially viable. Several challenges exist with this battery storage, such as safe disposal of the waste generated, unlike the case with pumped hydro. So, batteries will be useful in some cases, such as solar rooftop and frequency regulations, etc., but not elsewhere. Uh, Particularly for electrical energy time shift. So India has a large interconnected grid and providing storage at renewable energy site. So this would not be an optimal solution. Such individual site-wise deployment of storage can be very expensive. So grid connected pumped hydro is being adopted the world over for reasons such as electric energy time shift. So as discussed, energy storage technology have been compared in terms of duration, maturity, and application here. And different types of storages have been identified with this. So this energy storage is transformative technology, which may have a significant impact on the uh, cost, initial capital cost, and their lifespan. So, based on these two aspects, the energy storage systems are taken care. These storage technologies are decided based on their capital cost, charging and discharging time. So, this charging and discharging time uh, can be related to their storage of energies as well. So here we are depending mostly on their batteries for storing and discharging. So this uninterrupted power supply quality, transmission distribution for the grid support for load shifting and the bulk power management are decided based on the charging and discharging time. So next is the uh, energy storage this can be used in multiple applications. So this energy storage is not only used for balancing or stabilizing the load or the grid stability. This can also be used for many other purposes, transmission and distribution deferral, backup power, system peak shaving, load management, voltage or reactive power support, excess wind or solar generation. So this also can be used for energy storage. When we talk about this transmission and distribution, this deferring need for expensive upgrade to transmission and distribution network by storing excessive energy and discharging it during peak demand period. Uh, Transmission and distribution deferral can be benefited. Next comes the backup power. and system peaks shaving. During peak demand time, electricity prices tends to rise due to increased need of power. So this energy storage system can discharge stored energy during this high demand periods, thereby shaving the peak and reducing the need for expensive high carbon emissions. Similarly, for load management, voltage or reactive power support, excess wind and solar energy generation, ramping spinnings reserve, arbitrage. So these diverse application of energy storage underline its crucial role in modern energy management. Next, as we look for the future of energy storage, uh, we stand at an exciting juncture. Energy storage technology are poised to transform the energy landscape, this playing a crucial role. Technology advancement, which is the next generation of batteries in the horizon, including promising innovations like solid state batteries. So this can offer a high energy density with the replacement of traditional lithium ion battery. So other deployments such as lithium, sulfur and flow batteries are also emerging as strong candidates for large scale long duration. And as the share of renewable energy source like solar and wind continues to grow, the challenge of intermittency must be met. So, energy storage will be vital for storing surplus renewable energy uh, and providing power during the peak hours. Next comes the climate impact and decentralized energy system, cost reduction, and energy storage. So when we talk about the decentralized energy, the shift from centralized energy production to modern decentralized model is a significant trend. So the community energy storage system and microgrid are becoming more common. Energy storage future is closely tied to the development of smart grids nowadays and the use of artificial intelligence. These technologies can enable real-time management. Uh, so next is the three interlinked dimensions that are guiding role to energy storage in the electric grid. So when we talk about this renewable energy integration, uh, most crucial is supporting the integration of renewable energy into the power grid. So while sustainable and essential for reducing carbon emission, it is inherently intermittent. So energy storage system such as this batteries, pumped hydro flow batteries enable us to store excess energy generated during periods and released it during non-peak hours. So this type of storage system also facilitate a smoother and more predictable energy supply, allowing for a more balanced energy system. Next comes the grid optimization. As the energy landscape evolves, the electric grid faces increasing complexity. So, the integration of decentralized energy resource, renewable generation, and changing consumption pattern demands new level of flexibility, reliability, and resilience. So, another critical function is the peak shaving. So, during peak demand period, energy storage can be discharged to reduce the load on the grid. So, prevent the blackouts. So, furthermore, energy storage can facilitate grid modernization by enabling smart grid technology and more advanced grid management strategies. Electrification and decentralization support. So, global push for electrification and decentralization is reshaping the landscape as we move towards the electrifying transportation. So, next comes the grid stability and load management. So when we talk about the grid stability, with the rise of renewable energy sources such as wind and solar, we are naturally intermittent, balancing the supply. And peak saving is the crucial function where energy storage provides. So during the peak hours, we are critically concerned about the peak shaving and the load shifting as well. So these are the challenges faced by energy storage implementation. As we said before, cost consideration, efficiency limitations, safety and reliability, environmental impact and scalability are the general concern for all types of energy storage systems. When we talk about the policy framework and regulatory consideration, both developing and developed countries have their own policy framework where they are giving their incentives for the power purchasers and the other power developers like solar and renewable energy developers, where they can get the incentives from government, and tax credits and benefits can also be available to these types of power generators. And subsidies for deployment of these types of energy storage operation can also help to reduce the financial burden. So, which in turn, they can the private sectors, even both the private and public sectors, can avail for these types of regulatories for going to the energy storage systems. uh, Regulatory barriers can be like the existing regulations are not suitable for most of the energy storage systems when it comes for regulatory standards, clearance, environmental clearance, and social clearance for and ecological clearance for most of the power projects. So, regulatory barriers can also be a critical concern when we talk about the energy storage system. Next is the international standards, cross-border and regional cooperation. So, energy storage has the potential to facilitate regional power exchange, improving the resilience of interconnected grids. So, policy should encourage collaboration between countries and regions to optimize this energy storage to reduce and share best practices. So, these are the future directions and innovations. Next in technologies, research advancement, potential impact on energy systems, and commercialization efforts. So, on concluding this, these are the business models for consideration by power companies. So, this power purchase agreements and contracts, like when we say about power purchase agreement, renewable energy and storage power purchase agreement, and tolling and capacity contractors. So global energy sector is undergoing a paradigm shift, such as push for clean energy accelerates. So this power purchase agreement means to enhance the stability and reliance. 60% of the new power capacity being sourced from renewables are globally need for reliable energy storage, which has been more critical. Battery storage, which can store energy generated during peak solar and wind periods. So, when we talk about the contractor, another innovative model that has gained traction is tolling and capacity contractors. In the setup, buyer typically a utility or an independent energy provider pay the fixed fee to the to access and utilize energy from a storage system owned by a third party. So this model is attractive because it's allow power company to maximize the energy efficiency of their energy resource without taking on full financial burden of owning and operating storage assets. So as we conclude, uh, it's clear that energy storage system are not just a technical solution, but a fundamental a pillar for achieving climate resilience. By enabling stability, reliability, and efficiency, they form a backbone of future power powered by renewable energy. So, by adopting the best practices, it is essential for from carefully selecting the right technology to aligning with evolving regulations and fostering community engagement. And stakeholders across sectors, policymakers, industry leaders, researchers, communities must come together to drive this innovation to secure investment and implement impactful initiatives. So that's it. If anybody wants to ask anything or any queries, please let me know.
Thank you, ma'am. Thank you for the wonderful session. Dear participants, if you have any queries, you can ask, please. So no queries. So dear participants, if you have any query, you can contact ma'am and you can ask your queries at any time. Thank you so much, ma'am, for sparing your time with us.
Excuse me, ma'am.
Thank you, ma'am.
Yes.
Ma'am, this is Richard from K. Ramakrishnan College of Engineering, Trichy, ma'am.
Hello, sir. Hi, sir.
Sir.
Hi, ma'am. Ma'am, what will be the drawbacks when you integrate both two energy sources, ma'am? Said the batteries provide a high power density, whereas supercapacitors have a fast charging and discharging cycles is possible with the supercapacitors. When we integrate both the sources, what will be the challenges, ma'am?
So, as I said before, the challenge is mostly on the cost consideration and the integrating of two energy storage systems, sir. So
Yes,
when
ma'am.
we integrate two energy storage system, first the thing is it rely on the efficiency. We have to see on the efficiency and the cost consideration for combining these two technologies. So these are the barriers and the challenges faced for other energy storages as well, sir.
Okay, ma'am. Okay, ma'am. Thank you.
Okay, sir. Thank you.
Any other queries? Okay, ma'am. Thank you so much, ma'am.
Thank you. Thank you, ma'am.
Thank you so much for your wonderful session. So, dear participants, the feedback link has been posted in the chat window. Kindly don't forget to fill it. Your active session time as well as the feedback is must for the attendance. So, thank you, everyone. Kindly join in the same link tomorrow at sharp 6 p.m. Thank you so much.